With a coordinated turn under our belt, we can now develop trim trajectories. And a trim trajectory is just a desired trajectory and a very nominal behavior for the aircraft. This includes straight line flight, constant ascent, as well as moving in a constant radius, hence the coordinated turn. So we're going to go ahead and jump in and design these trim trajectories, which include both the nominal state and constant inputs for these trajectories. Okay, so let's go ahead and get started. So given a nonlinear system, x dot is equal to f of xu, and remember that we've seen this several times before. For us, we have u was generated by just delta E, so for our elevator, our aileron, our rudder, and our throttle. So we have our inputs u, and we use these inputs, we put them maybe in a block, and we said, hey, these inputs are u, they went into our forces and moments. And from our forces and moments, we got our body frame forces and our body frame moments, and we were able to put that into it along with our state. So our x was our position states. We also had our velocity states. We had our Euler angles or quaternion, and we also had our rotational velocities. So we put those states as an input as well into what we called our derivatives. If I could spell. And we got out our x dot. Excellent. So the combination of these two things, this is our f as a function to get out our dynamics, f of x u, and again that's equal to x dot or d dt times of x. So we've been dealing with this nonlinear function, and we expressed this nonlinear function at the beginning of this chapter. We saw that we have a significant number of nonlinear functions. So this f, when I say significant number, what I just mean is that f of xu was equal to, we had f1 of xu, so that's a scalar function. f2 is another scalar function on our east, right, all the way down to f12 or 13 xu, so 13 if we're using quaternions. So we have this function f, which defines the dynamics of our system, how our system is evolving over time. Now, there's a concept known as an equilibria. So an equilibrium point is defined as both a state and an input such that our dynamics are equal to 0. Now, we don't really care as much for our dynamics equal to 0 because we're not going to have our aircraft go somewhere and just stop midair, right? So an equilibrium isn't necessarily exactly what we want, but it's along those lines where we have this constant state, constant input, and we want to be able to have this nice condition. So an equilibrium is a trim condition. So in general, the trim conditions may include states that aren't constant. So for our example, our aircraft is moving, right? We want to be able to have our aircraft move. So our trim trajectory is going to be a moving trajectory. So what we do is we define our trim conditions. They're given by x dot, and we mark it with a star, is equal to x star u, f of x star u star. And we're going to characterize it, where in the trim trajectory, all the time derivatives Now recall for equilibrium, we said all the time derivatives are equal to 0. For trim, we're not going to say 0. We're going to just say that they're constant. Oops. Where did my... Are constant except Pn and Pe. So now we have constant motion. I'm sorry, we have constant motion, and it's going to cause our derivatives to be constant except for Pn and Pe. So those things can be varying with time. So we have these nice constant derivatives, and we can define it in terms of 3 variables. The first is our VA, and we'll mark it with a star. Second is gamma star, and third is our radius. So again, our trim trajectory is that all of our derivatives are constant. So 0 is a trim trajectory, but not a very interesting one for an aircraft. So we'll go ahead and design it. And when we're designing our trajectories, we're going to assume that there is not any wind. So when wind is 0 and side slip is 0, so those are the conditions we're looking at. Our VA is equal to VG, so our airspeed is equal to the ground speed. And then our velocities are equal to, well, in reality, these 3 are stating the exact same thing, right? So we had that VAB was equal to UR, VR, and WR. And we had VG in the body frame was equal to UVW. So we've really only just swapped the sides for some reason. Another condition that holds is that our heading angle is equal to our course angle, and also that our flight path angle is equal to the Air Master's reference flight path angle. So these are all the simplifications we're going to use when we're developing these trim trajectories. Okay. Again, like I mentioned before, our trim trajectories are defined by 3 parameters. So we're going to say that we're traveling at some constant speed. So the fact that this is a constant speed is very important. So we will define the speed that we want to be traveling at. We're going to be climbing at a constant flight path angle. So if we look at level to V sub g, right? Remember that our flight path angle gamma, that's going to be constant. And again, we're going to be orbiting at a constant radius. So once all these 3 parameters are defined, then we can go ahead and define our trim trajectory. Okay, and recall, in this case, we're going to be we'll use our Euler representation because that was really how we defined our coordinated turn. Okay, so let's go ahead and look at how do we calculate our trim. So we're gonna try to define everything that we can. So if the speed of our aircraft is not changing, that would mean that our U dot, V dot, and W dot are going to be equal to 0. So our aircraft speed is not changing. And remember that doesn't mean that our aircraft can't go in a circle because these variables are defined in the body frame. So our aircraft speed isn't changing. The roll and pitch angles are going to be constant. So again, a constant value for our roll will give us that coordinated turn, a non-zero value will, and the pitch will give us that vertical movement. So since our roll and pitch angles are constant, we're going to also, that's going to mean that our P dot and Q dot are also going to be constant. So here we see that 1, 2, 3, 4, 5, 6, 7 of our equations in our dynamics are going to be equal to 0. We're also going to, not listed here, is we can say that our translational, our side-to-side velocity is 0. So we're not slipping. So what that means is that v is equal to 0. So recall that v is our velocity in the y-axis on the body frame. So going out the wing, our velocity is going to be 0. Excellent. And so then we would say that VA squared, which is equal to, is going to be equal to U squared plus W squared. Now, we should have a plus V squared, but that's going to be 0 per that condition. Okay. So we don't have to worry about that. We'll just say that our airspeed, the square of our airspeed is equal to U squared plus W squared. So that's just a relation that helps us obtain our airspeed in terms of the states of the aircraft. Excellent. So then when we have our coordinated turn, we have our turn rate constant. So this comes from our coordinated turn model. This helps us relate our yaw angle with the radius that we want to move in, the airspeed, as well as gamma. Gosh, for some reason I cannot remember our flight path angle. So it keeps slipping my mind today. And then we also want to climb at a certain rate. So if we look at, this is our desired VA or VG, right? We have gamma. So our upwards velocity is just going to be equal to VA times the sine of gamma, where these are both the nominal aspects. So H dot is equal to VA sine of gamma. So then we can define what we want as our nominal time derivative for all these states. And again, we're going to be using our Euler coordinates. Okay, so if we start to look at this, we have our north, a velocity in our north direction. We really don't care about that, right? We're moving and we don't care. We also don't care about the east direction. We have H dot. Now this is often a sore point. This is equal to negative PD. So if you're to put in a PD dot, that's going to be a negative VA sine gamma. Okay, and then we have all these 7 values come in here. So we have U dot, V dot, and W dot, as well as P dot and theta dot. Those are all going to be equal to 0. We also have that P dot and Q dot are equal to 0. And we could have also said that our R dot is equal to 0. So we're changing our yaw also at a constant rate. Okay, so this is our desired, again, this is the desired / our trim dynamics. And we don't care about the top 2. Excellent. So now we just have to, all we have to do is calculate it, right? To do so, we're going to use optimization. So we'll throw this into an optimizer and have the optimizer figure out what do we need to, what are our states defined as, and what are the inputs. So what are the elevator angle, the aileron angle, the rudder angle, and the throttle. Okay, so we're going to define an objective function that'll help us calculate that trim state. Again, we've calculated what we want our dynamics to be, but we haven't defined what any of our states are, and we haven't defined what our inputs are. We just know that our dynamic equations have to equal these equations, so we've put there on the board. Okay, so let's calculate our trim using optimization. So we're going to just call this function FD, right? So it's a function of our variables, it's the desired value for our dynamics. Sorry, I don't know why that was so hard. Okay, given a particular choice, a choice for x and u, we can calculate f of xu. Okay, then we can compare it. We can then compare this to our FD, our desired value for our dynamics. Okay, so to do that, we're going to let this delta be equal to f of xu minus FD. And I actually wrote it backwards in my notes, but that's fine. So we can, then the goal will be is to choose x and u such that this delta goes to the 0 vector. So we want delta to go down to 0. So what we need to do is so the approach we're going to take is define a function that is 0 when delta is equal to 0 and non-zero or positive otherwise. So if you think that about the shape of that, a quadratic is a really nice shape describing that exact function. So we have our minimum value is at the desired, delta is equal to 0, and then everywhere else is positive. And if it's nicely shaped, also that'll help us converge better. So we're going to define a function j, and it's going to be a function of delta. And we'll just say that this is equal to delta transpose q times delta. Now this is just a generalized quadratic equation, right? So it's going to give us that shape that we want. But we're going to be just a little bit more careful how we design this. We're going to say that we really don't care about those top two. And in actuality, this one is very sensitive. So if we're going to have any error, we don't want to have any error in that one. So we're going to let Q be equal to a diagonal matrix, 0, 0. And then we'll start putting ones everywhere until we get to the component that corresponds to psi dot. So the 1, 2, 3, 4, 5, 6, 7, 8, 9th. The 9th diagonal element. And we'll just let that one be equal to 1e to the 9 or something like that. And then 1 down to 1. So we're going to just really penalize convergence to that one. And that's just to make it sensitive. So again, these two elements right here, the upper two show we don't care about PE, and PD. Oh, not PD, PN. So we don't care about those two at all. And then this 1e to the 9 is that we care a lot about psi dot, because psi, that's very sensitive to any deviations from that. Okay, so now if we define this function j, we know that we want j to go to 0. So we're going to use optimization to force it to 0. So we'll optimize, and we'll say that our x star u star is going to be equal to, we're going to take the argmin, so the resulting parameters that cause the minimum, of j, of this delta, where delta is defined in terms of x and u, right? And yeah, so we just have delta defined right here, such that, and we're going to define all of our constraints from the previous slide, right? So we have a host of constraints that we can employ. So we're going to say that our P is equal to 0, so that's one of our states. Q is equal to 0. We have that VA squared is equal to W squared plus U squared. We have that V is equal to 0. We'll just let our Pn equal to whatever the desired value, our initial value was for that. So whatever we want, really. We'll say that also our PD, our PD is going to be whatever desired. And also our psi doesn't show up anything else, so we can just say that that's going to be whatever, some nominal value. And we'll also constrain it, and we'll say that phi is going to be in the interval negative pi halves to pi halves. So that would be corresponding to a bank angle all the way down, so we don't want to do any more than that. Theta is similarly, we're going to be just a little bit more careful with theta and say that we can only go to pi halves minus some epsilon, some small value. Just because once we go straight up, then our dynamics have a singularity, which is problematic. We'll also say that our delta E, delta A, and delta R are in the interval negative pi halves to pi halves. And we'll say that our delta T is in the interval 0 to 1. Okay, so this is then the optimization problem that we can plug into a standard optimizer, and it'll then produce our desired trim state and trim input. Where again, remember the trim state is going to be these values, and our trim input is going to be these guys. So we can define that optimization problem, and then the optimizer will produce the trim trajectory for us. Okay, now let's take a look again at this sim. So here I just entered a value for 25 for our desired velocity. So it had been at 35 down there, and now we jump down, and we're doing our input of 25 meters a second. And we see that since we have gamma is equal to 0 and our radius is equal to infinity, which is what a negative number corresponds to, what we can see is that we're just traveling in a straight line, and we can see that it's fairly straight. We're going in that north direction. It's just increasing linearly with time, ideally at that slope of 25 meters a second. But what you'll see also here is that now in our y-axis, we're starting to see some deviation. So we were good for quite a bit of time, and then we started to see some deviation. In our z-axis, we're staying up close to 0, but we're actually starting to dive just a little bit. When I previously run the simulation, had run long enough to go down to negative 20,000 meters, so pretty high. Okay, so that's really excellent. Let's jump and have our gamma equal to something so that we're actually moving upwards. And now we need to wait until this bottom comes off. But what we can do is we can look at a couple things. We can look at our theta, right? And so our theta, we had some nominal desired value. We can see that being pumped in here. And we can see that our psi is staying around 0 and our phi is staying around 0, or at least it was nominally, until it starts to get off of its desired course, because we have no control keeping us back. Okay, and now that our z is back to something we can see, we see that we're increasing linearly with time in the z-axis, but now you'll see we're starting to fall off as we're falling away from our trim trajectory. So let's bring it back. Maybe we'll change the velocity to 24. So restart it. Okay, and you'll see again. So that was just a hard reset to all of our states. So we start to climb linearly, and you can see back where we're getting close to these nominal values. So we've defined nominal states. That's where we reset the aircraft to, as well as nominal inputs. Now, if we change our radius, right, we'll see now both our x and our y will start to change, right? Once it's reset, we'll still be able to climb in the z direction, and we'll see that. Let's bring back the aircraft. We'll see that it now starting to fall off its trim trajectory. So now we're starting to go back down. Okay. Some fun things to look at, again, is if we have our, let's change our velocity to something small. And even we'll have no vertical direction. We have our aircraft will basically be going like this to try to get some more extra lift to stay at that constant vertical value. So we wanted to stay even. It required our aircraft to be traveling like this. Okay. And the faster we go, the less of that angle we need. So if we go down to 35, we'll see that we're flying nearly straight and we have enough lift to keep us going up. This is really cool. We can define these desired trajectories using these three parameters, and we'll get the nominal state and nominal inputs out of the optimizer. So really cool. And just kind of going that straight. And one other thing to note is that the straight trajectory is the one that'll keep us. We can execute that straight trim trajectory a lot longer than we can with anything with a non-zero gamma or a non-zero radius. Okay. Perfect. All right, so there you have it. Now we can create these trim trajectories.